Good evening, everyone. Can someone confirm whether I am audible today properly or not? Today it looks like my net is back. So just wanted a confirmation whether I am properly audible or not. Okay, great. Great. So I think we will go uninterrupted today. So I'll be quickly walking through some of the things that we have done in the last class where there was some disturbance. Okay. So I think from the week before, from the class before yesterday, so before day before yesterday. So in the last full class, we have actually focused on. So if I put here 23rd. So from the last class onwards, we started building the models, machine learning models, right? And we started off with the basic perceptron model. And we have discussed that how do I really evaluate. So basically, we have divided the data into training data and the testing data. And because of that, to bring uniformity, we are building the model on the training data, and we will test the model on the testing data. And on the test data, we will go for different kinds of metrics. And based on how the model performs based on different metrics, we will typically give our final verdict on which model is the most appropriate model. So the basic perceptron, we know it's a very, very basic model because here the output of this model is only two values, 0 and 1. Whereas from the next model onwards, let's say the logistic regression model, we will talk about the probability, right? We will talk about belonging to a 0 or probability of 1. So we generally talk about a probability, especially when we are going to discuss the remaining models from now onward, from the next model onward. Whereas this basic perceptron does not give the probability, it uses a step function as we have discussed. So because of this step function, it will only give an output of 0 or 1, no intermediate. So there is nothing called probability or anything given by it. And because of that, we will see that the convergence of the model will be a big problem. All right. So what did we do? Okay. So now let's assume that we are, so the steps wise, probably once you build the next model, we'll find we are doing the same steps. Initiation of the model, then fit the model on the training data. For some models, we can check the coefficients, but obviously we may not be more interested in knowing about the coefficients, right? Then we do the scoring of that model back on the training data. The intention is to understand whether the score is better than the null score or the default score. What is the default score? Just try to look at the distribution of zeros and ones in your training data and look at the maximum class. So 2375 divided by 2375 plus 453 giving me approximately 84%. So what are we saying? 84% is the null accuracy or the default accuracy of the model. So any model that I am building, especially if I am testing it back on the training data, I want the accuracy to be more than 84% when I am testing it back on the training data. Right? Here it is only 78%. But any model that I am testing it back on the training data, I require an accuracy of at least 83.98%, if not more. Otherwise, we will call that model as an underfitted model. So underfitting we have already discussed. I'm trying to use a simple model when the problem is a complex problem. So here, logically speaking, I could have scrapped the model here itself. But because I have created a kind of a generic framework altogether, here it is not getting dropped. Then we'll use that model to predict on the testing data. Now in the testing data also, you can very well see how many defaults and how many non-defaults are there. We could see approximately 85% of the people are non-defaulters, which is more or less a similar proportion between the training data and the testing data. Now we have run a few metrics on the testing data. What are the metrics? Generally, we talk about the first metric could be a very basic metric called accuracy of the model. But all these metrics are derived from what is called as a confusion matrix. All these metrics are divided from confusion matrix. We have already defined the confusion matrix in detail. Right, we have defined the confusion matrix in detail. You can take the predicted values on one side, where the predicted value could be a 0 and a 1. You can take the actual values on this side, where the actual value could be a 0 and a 1. So I have already talked about this is called true negative, this is called true positive, this is called false positive, and this is called false negative. These are some of the things that we have already defined. Now, in our case, we have got these numbers 943. So because every time a random variable changes, so somewhere the change comes. So 943 is the value out here, then 90, then 163, and finally it is 60. So this is what we got by using the basic perceptron kind of a model. So when we compute the accuracy, we only talk about both the true. So the accuracy is nothing but true positive plus true negative divided by all four, which is true positive plus true negative plus false positive plus false negative. So this is actually talking about the overall accuracy of the model. And this measure will be a good measure if my outcome variable or the target variable is well balanced. If my target variable is well balanced, this model, this measure, this metric would be a very good metric. But in our case, if we see, almost 85% of the data is zeros and only around 15% of the data is 1. So this data is not balanced that way. So this is called an imbalanced data. And whenever we have imbalanced data, probably accuracy should not be the first priority in comparison across the model. Now, The second measure that I am talking about here is a measure called F1 score. The F1 score internally uses two measures called precision, and the second one is called recall. Recall has some other name in some other context called sensitivity. Right? So what happens, both these recall and precision, they are based on only the events occurred. They are more bothered about only the events occurred, which means only the ones. They are not at all bothered about the zero group. You will find that, right? They are more bothered only about the group 1. So, which means they are more bothered about the true positives. To be more clear, they are more bothered only about the true positives. So, while one of them looks at, so precision, if I see, it looks at true positives as a ratio of the total predicted positives. So the predicted positives is this one. So as a percentage of the total predicted positives. So in our case, it is 16 out of 90 plus 16, 106. What does this mean? Okay, our model has predicted 106 people that they would be defaulting. Our model has predicted that 106 people will be defaulting. But how many of them are correctly predicted? So, and how many? There could be many wrong predictions. You have predicted 106 people will default, but probably coming out to 15%, 15.09%. So this is around 15.09%. Whereas the other measure, which is called as a recall, it looks at the predicted positive out of the total actual positives. So if I look at it, this is my actual positives. So 163 plus 16, 179 of them are actually positive. But out of those people who are actually positive, my model has predicted only 16 of them that they will default. The remaining 163 of them, it has predicted that these people will not default. So sometimes called as a sensitivity also, the recall and sensitivity, they talk about again the prediction of 1. So in this case, we could see that that ratio is only 8.9%. That ratio is only 8.9%. So generally these two are taken together and this F1 score is computed, which is otherwise called as a harmonic mean between the precision and the recall. So if I do something like this, 2 times the precision times the recall divided by precision plus recall, that is what is going to give my F1 score, which happens to be 11.228%. So frankly speaking, this is a much better model of accuracy, especially if I have too much of imbalance in the data. I can very well go with the F1 score. So any model that is having a higher F1 score compared to my compared to the other model. So we can compare the F1 scores across the model. So whichever one is giving the highest F1 score, that model could be a more preferred model. Now, the third measure that we can think of is what is called as a Cohen's kappa score. Now, this is a very interesting measure, right? The way it looks at seeing it is, so normally there is a kind of a default accuracy that can come. So what is the kind of default accuracy? So for that, what the Cohen's kappa simply looks at is, it goes with your, so just like the way you do in a chi-square test, you look at the chi-square value and you would see how much. So what is the independence between the true positive? Now here, so independence, initially we compute what is called as a null accuracy here. The null accuracy or a default accuracy, right? You can use either of the words. The default accuracy or a null accuracy here is computed by considering the predicted and actuals are independent. So the default accuracy is computed by assuming that the predicted and the actuals are independent. So what does that mean? When I have to say these two are independent, we can look at it: 943, 90, 163, 16. So that is the default accuracy. Okay. So you can very well find out the row totals and the column totals. So this is what we do in a typical chi-square test analysis as well. So this one becomes 1033. This is 179. Whereas this side it becomes 6 and this becomes 106. Right? And overall it is 1112. So what we find out, when both these row and the column are assumed to be independent, we can get the expected values. We can get the expected values for each quadrant. How do I get the expected value for each quadrant? I take the row total multiplied by the column total divided by the total. That is the expected value for each quadrant. So for this quadrant, if I need the expected value, the row total is 1033 multiplied by the column total is 1106 divided by the total is 1212. So it can come out. So probably, I mean, this is running here. So probably I'll do it in calculator. Okay. So we are taking the row total to be 1033. So 1033 times 1106 divided by 1212. So this is coming out to 942.655. Okay, so we are very close. So it is coming out to 942.655. Similarly, for the next quadrant, it is 1033 into 106 by 1212. 1033 into 106 by 1212. So this is coming out to 90.34, which is also looking more or less similar. Then this one comes out to be 179 multiplied by 1106. So this one is 163.34. So we are more or less close here. And probably we can talk about the last one being 179 divided by 106 divided by 1212. This is coming out to 15.65. So what we are simply saying is the null accuracy or the default accuracy for me is, now look at these two, right? 942.655 plus 15.655 out of the total 1212. So the default accuracy is coming out as 942.655 plus 15.655. So 958.31. I divided by 1212. So the default accuracy is coming out as 79.068%. So this is what is taken as the default accuracy, assuming that the predicted and the actual values are independent. The overall accuracy is computed. So this accuracy is called as the default accuracy using the Cohen's kappa metric. Now what is typically done? So even if there is no dependency between predicted and actual values also, my accuracy can very well be 79.068%. So what I really want to look at is by how much extent my actual accuracy, my model's actual accuracy is greater than the default accuracy. So what was our actual accuracy of our model? Actual accuracy is 79.125%. 79.125%. Whereas the default is 79.068. So that is the difference. So what is called as Cohen's kappa score here is 79.125, which is the actual accuracy on the testing data, minus if at all they were considered independent, I could have got an accuracy of 79.06, which means this is the difference is the actual performance of my model. Now, I want any kind of a performance over and above this. So, which is what we say 1 minus of 79.068%. This is what is typically called as your Cohen's kappa. And this value has been only 0.27%. This value is hardly 0.27. So normally, if this Cohen's kappa is very, very high, even this value can go very close to 100%, right? But we are at only 0.27%. Probably it looks like very much on the pathetic side. So when there is this model is a much more sophisticated model, especially if we are having too much of imbalance in the data. If I have too much of imbalance in my target variable, I can very well look at the Cohen's kappa. I can compare the Cohen's kappa across the different models, and based on that I can shortlist which model is the best model. So this is my third metric. So we said one, we can look at the accuracy, which could be a very basic metric. Two, you can look at the F1 score, which is a much better metric. Three, we are also looking at the Cohen's kappa, which is much more sophisticated. And the fourth one is actually called as the area under the ROC curve. I will talk about it in the next model, because in this model it's very difficult to get that area under the ROC curve, because this model here does not talk much about the probabilities. This is a kind of, as I told you, any model that predicts the probabilities, for that model the area under the ROC curve is comfortable for utilization. But whichever models don't predict the probability, here there is no prediction of probability. Here it is only the 0 or 1 that is predicted by using the step function. No question of probability being predicted here. So that is the reason I cannot plot the area under the ROC curve. So I can't compare this model with the area under the ROC curve. But when I take the logistic regression next, right? I think in a few minutes I'm going to start on the second model which we are going to deal with, which is the logistic regression model. But in the meanwhile, let me quickly see if I have missed out on any of the metrics. So that's the reason I have hashed out these two things, because it does not give the prediction of the probability. But other metrics I have discussed in detail, and these are the ones that are printed, those metrics, right? So these are the calculations. So probably we can ignore them as well, because I have already shown those calculations to you. Okay. So with that, we enter into the logistic regression, which is the second model. But in the meanwhile, if anyone has any questions on the first one, I want to first address those questions till whatever the concepts that we have discussed. If anyone has any kind of questions, I want to first address them before I move to the second. In the second model also, see, from the second model onward, or probably in the second model, we'll discuss a few more concepts. We will apply that cross validation. We will apply the hyperparameter tuning, etc., which we discussed, parameter tuning, etc. So some extra concepts are going to be discussed in logistic regression as well. But from the third model onward, only the basic mathematics of each of these models will be discussed, because the coding part of it is more or less the same. So we will run the code and we will try to look at the comparison across the model. All right. So yeah, if there are any queries on the first part, let me try to address them. Otherwise, I would directly start off with some basic background regarding the logistic regression, and then we will try to implement the same. Can you please explain the confusion matrix once? Confusion matrix contains 4 elements, right? I think you may have to go back and refer to this video, because over the last 2-3 sessions, I have been explaining this confusion matrix. So you just need to know that these are the 4 elements. This is the true negative. This is the true positive. This is the false positive. This is the false negative. So generally, whatever you have predicted, this is zeros are called negative and ones are called positive, because they are the events, right? You have predicted these as positive. but out of them, 16 of them are really positive, whereas 90 of them are actually negative. So you have done a false prediction of them. Similarly here, these are the negatives. Okay, I did not explain balanced accuracy. Okay, I think I have a fourth metric to explain. So then here we have predicted negatives, and out of these negatives, only 943 of them have been correct negative, whereas 163 of them are actually positive, but you predicted as negative, which means your model has predicted that these people will not default, but in reality they have defaulted. Does that sound good, Madhava? I think you may have to go back and listen to the video once again, right? That can give you a little bit of more clarity. I think I have missed out on one more metrics, right? Probably you can call this area as a 4. The fifth one is called as a balanced accuracy. So these are the 5 metrics you can use for all the models, and based on the comparisons, you can very well shortlist on. So balanced accuracy metric, right? So the balanced, what it does is, the balancing it does based on 2 things. One is called as the sensitivity, which is the same as recall. Recall and sensitivity are one and the same. Sensitivity plus specificity, one more computation is coming, divided by 2. Now, as we have discussed, sensitivity is nothing but recall, which is nothing but true positive out of the total actual positives. Actual positives actually contain true positive and false negative. Similarly, the specificity, we have already computed the recall. The specificity comes out as the other way, the negatives. True negative out of the total actual negatives. True negative by false positive. So out of the total non-defaulters that are there, how many of them have been identified correctly by my model? That is what is specificity. So in this case, the specificity is going to be 943 divided by 943 plus 90. So this ratio looks like a much bigger ratio, better ratio. So we can very well find that out. 943 divided by 1033, which is 91.287%. So zeros wise, it might have done a good job. But when it came to ones, it did a very bad job. Our recall was hardly 8.9%. So sensitivity is only 8.9%. So when it comes to balanced accuracy, we are saying 8.9% plus 91.2 or 3% divided by 2. So that is where I think you would have got 50.11%. So even this can very well be used if there is a lot of imbalance in the data, right? So normally don't use accuracy as a measure for comparison. If you are seeing a lot of imbalance in your data, ignore that, because it might very well come out that the accuracy is 90%, 85%. You may be tempted to really say that this model is a very good model because it is giving an accuracy of 84, 85%. But in reality, the default accuracy itself could be that 84, 85%. So there is nothing much that my model is contributing here. So that's the most important element, especially in all these fraud models and the bankruptcy models, etc., the events are very few in number compared to non-event. And because of that reason, accuracy would always be a misleading measure. You should always look at these. So I am giving you overall 5 different metrics. Of course, area under the ROC curve may not be applicable for this particular model. All right. So these are the various metrics. I hope no one is having any questions. So I'll move on to the next model. Possibly, if possible, I'll try to finish off the logistic regression today. Okay. Now, I want to talk about a few important concepts. So basically, for every model, I will spend some time in terms of discussing some basic concepts, very basic concepts about the model. Then we will go ahead and look at the implementation of the model. So though the word actually regression is present in the name, this is still a classification problem. It's not a regression problem. Right. So logistic regression also, the name contains regression in it, but it is a model that will address a classification problem, which means my target variable should be either a binary like this, or it could be multiple categories, right? So C1, C2, C3, it could be multiple categories and grouping or classifying the data into one or more of these categories. So your target variable is a categorical variable, and your feature variables could be any. They could be a categorical or numerical variable. Now, one of the major differences between the basic perceptron model and the logistic regression model is this model is going to predict the probability that a particular record or particular observation belongs to a default group, and what is the probability that it belongs to a no default group. So rather than directly classifying as 1 and 0, it actually puts a probability that it belongs. So the modeling that this logistic regression model does, it models the probability of belonging to a particular group rather than the actual group, right? So here, first of all, we have to define what is called as a logistic function. I want to define something called a logistic function. The logistic function simply says y is 1 by 1 plus e to the power minus x. This is what is a logistic function. And why we are interested in this function is when I look at the plot of this function. So for any value of x, you take any x, right? You take any value of x, you will find that the y will lie between only 0 to 1. That's a major benefit of this logistic function. Of course, there are a few more such kind of functions, right? So we will see that this logistic function 1 by 1 plus e to the power minus x. For example, if you see x is a very large value, let's say x is tending to infinite, then my y 1 by 1 plus e to the power minus infinite is going to be 0, is going to be 1. And x is going towards minus infinity, right? So e to the power minus of minus infinity is e to the power infinity, which is a very large value, 1 by infinity, which is going to be 0. So when x is going very close to minus infinity, y is going close to 0. If x is going close to plus infinity, y is going towards 1. So this entire, and if let's say, just for example, I take x is going towards 0. Then what about y? 1 by 1 plus e to the power 0, which is 1 by 2. So y is between 0.5. So for all negative values x, for all negative values of x, y will be less than 0.5. And for all positive values of x, y will be greater than 0.5. So you could clearly see that the entire day getting reason why say we can make is going to be a kind of a probable one that we are going to predict is going to be what is called as a probability. We are not predicting any value. Let me just check. Is it still a problem? Okay, let me explain the next statement. In case it is stuck, you can again tell me, because my network is looking like. So my network is looking pretty much fine. I don't know why it is breaking. Let me switch off my video to see if some improvement can come. Now you can tell me whether it is fine or not. Okay, then I'll continue without my video from now onwards for the remaining part of the session now. Okay. Okay. So first, let me work on this part. So the logistic function can actually, whatever is the value of x, the logistic function can bring a value within the 0 to 1 kind of a range. So that's where what we say is we will not predict the value. We will predict y hat, which is what is a kind of a probability of belonging to group 1, of getting an event, probability of occurrence of event, which is the probability that your target value will take a value of 1, means the default will occur. And till now, whether it is in the various linear regression models or even in the basic perceptron model that we have discussed, we have been using the mean squared error as the error metric. Now here, I cannot use the mean squared error because it does not predict the actual value. It does not predict the actual value. It predicts the probability. So it does not predict 0 or 1. It predicts the probability that the value that the observation belongs to group 0 or the observation belongs to group 1. So here we will introduce another error metric. Right? We will introduce another error metric. We cannot use the mean squared error here. So for all the classification, for majority of the classification model, we can very well rely on this error metric. We are going to talk about the log loss function, right? Probably a little bit later, I'm going to talk about that log loss function, right? So whatever is the advantage of this model is, whatever the output that you get in the linear regression model that you have taken, so that linear regression output will get translated. So this output that comes from a linear regression, it goes in the place of X here. The output that comes from the linear regression, it goes in the form of X here and gets translated into my Y, which lies between 0 to 1. Right? So generally, when there are only two values in the dependent variable, that is what we have, right? Default, no default. Only two values are there. Probably even though they are numerical, because we have converted them into dummy variables and the values would have become 0 and 1, but still the linear regression would not work in this case, because linear regression assumes that my variable is normally distributed. So you can very well treat y-axis as the probability of belonging to a particular class. So you can very well say, if at all my probability of y equal to 1, if it is greater than 0.5, then you can very well say that the person had defaulted. So manually you will put them into group 1, and if the probability of y taking a value of 1 is less than 0.5, you can very well put them into a 0 category, saying that the event did not happen. So the decision is coming just as a kind of cutoff. You put some cutoff on the probability, and based on that, we are simply taking the decision. So for example, I just want to compare the linear regression with the logistic regression. I want to compare linear regression with the logistic regression. In the linear regression, we were talking about our target variable, right? Probably we were calling as a plus b1 x1 plus b2 x2 plus and so on, Bn, xn. So this is what we have done as a linear regression prediction, right? So now what is that we are saying? I have my logistic function, or sometimes this logistic function is otherwise called sigmoid function. Now, sigmoid function, we are simply saying 1 by 1 plus e to the power minus x. So, which means now what I am going to do is this y hat, right? I am going to look at this y hat as the sigma of, right? Now I'll take the sigma of all this. Right now I'll take the y hat in logistic. This is the y hat in linear. In logistic, the only difference is I will take the same b1, x1, b2, x2, whatever the variables that we have taken. I'll put a sigma on the top of it, which means it will become 1 by 1 plus e to the power of minus a plus b1 x1 plus b2 x2 plus so on bn xn. So that is what will become my y hat in a logistic regression. Right? Linear and logistic are more or less similar, but the only thing is here that value is converted into a probability between 0 to 1. Now, how do I solve this? Probably I can very well talk about a simple sigma notation here. 1 by 1 plus e to the power of minus, probably this a also I can write it as b0 x0 kind of a thing. So I can very well say I equal to 0 to n b0 times x0. So this is what is the typical notation. Now, this one, you know, here you can very well, if I do a simple cross multiplication, it will become y hat plus y hat times e to the power minus this entire thing, otherwise a plus b1 x1 and all, I'll call it as some z. Y hat times e to the power of minus z is equal to 1. So based on this, I can very well find out what is going to be, right? I can very well find out that e to the power of minus z is equal to 1 minus y hat by y hat. And probably if I'm turning it over, minus z is equal to log 1 minus y hat by y hat. And taking the minus on both sides, z is going to be log y hat by 1 minus y hat. This actually is nothing but the odds of occurrence of an event. This is odds of occurrence, because if you remember, if the probability of occurrence, in your probability course you will read this, if the probability of occurrence is P, probability of non-occurrence of an event is 1 minus P, then the ratio of probability of occurrence to the non-occurrence is nothing but the odds of occurrence of that event. We have already said that the probability of occurrence of a default is y hat. So the denominator is probability of non-occurrence of a default. So the ratio of these two is nothing but the odds of occurrence of the default. So that is where what we say is we are modeling here nothing but the log odds of occurrence of an event. Okay, so if you are not understanding this, also not a big deal. But if someone wants to understand the mathematics or the concept behind the logistic regression, I'm just giving some basic intuitions into this. Otherwise, you may not require because you can very well run it on the Python program and you can very well compare using those 5 metrics that I have used. So normally here, the loss function, the error function, it's not a mean squared error. In the linear regression and the basic perceptron, we were using the error function like this, right? 1 by 2m sigma x minus or y minus y hat whole square. This is what we have been using as the error metric. Now here, what we say is we use something called the log loss function. And we would be typically minimizing the log loss function. So the way I can define this log loss, we'll spend some time, minus 1 by m times. So for each of the observations, so I'm putting a sigma from 1 to m. The y, which is the actual y. Actual y values would be, so I'll say yi. Actual y value would be either a 0 or a 1. Multiplied by log y hat of I. So y hat of I is a probability, right? Y hat is a probability of occurrence of that event. So y hat, yi times log y hat of I plus 1 minus yi times log 1 minus y hat of I. Now, just try to understand it. So this is what is going to be my loss function. Now think of it, right? We'll try to see what is happening. If yi, the actual value is 1. And let's assume that the predicted value, which is the yi hat, is coming close to 1. Then what would be the error? So this is a probability. So we are saying close to 1, if not a perfect 1. So if it is coming close to 1, obviously the yi hat logarithm of 1 will become 0. So this term is completely becoming 0. Similarly here, if yi is 1, 1 minus yi will be 0. So this term also will be 0. So obviously we are finding error equal to 0. When the predicted and the actuals are very much around 1, the error is 0. Similarly, you think of it, if the actual value is 0 and the model predicted probability is also coming out to 0, right? Obviously here, if yi is 0, this whole term is becoming 0. And so when yi hat is also 0, obviously 1 minus yi hat is going to be somewhere around 1. So you will typically find log 1 is 0. So when both of them are almost matching, you will see that the error is 0, right? So that is the reason what we say is for all the classification models which are going to give probability as their output, probability of belonging to a particular event, probability of occurrence of a particular event. So any of these models which are going to give the probability of occurrence of an event as the output, we can very well rely on this log loss function altogether. So this is one more new function, right? So error functions wise, we have looked at MSE, mean squared error. Right now we are going to look at log loss, and I'm sure for almost all the classification problems that we are going to look at, log loss function is the most appropriate kind of a function. Okay, so I think that is the basic. So anyone, of course, the conceptual part, I'm just giving some basic concepts. I mean, obviously, we can't cover all the things. Here, the focus is more on the Python implementation of the same. But at the same time, a little bit of mathematics, whatever is required, I try to explain it in a short. So this is what I'll be doing for almost all the models, right? So there could be some gray areas for some people, but definitely for that, you may have to refer to some additional or you try to contact me separately. Okay, so this is how that logistic function looks like, right? You see, whatever is the value of the x that you are taking, this logistic function lies only between 0 to 1. The minimum value is 0, the maximum is 1. And probably when the x value is around 0, the y is somewhere around 0.5. So for all the values of x which are negative, the probability will come out to be less than 0.5. And for all the values of x which are going to be positive, the probability of the default occurring is going to be more than 0.5. So this is how you can look at plotting. So what are we saying? We have taken so linspace. We have used this function when we talked about the numpy features. So from -100 to +100, right? From -100 to +100, I am taking 1000 values which are uniformly distributed. So we have a -100 here. We have a +100 here. So between -100 to +100, I am taking 1000 values which are uniformly distributed between the two. Then I am computing 1 by 1 plus e to the power of -x. That is what is the definition of my logistic function. So I am computing that. Then I am plotting a figure. In that I am plotting the t values on the x-axis and the sigmoid values on the y-axis. And giving the legends and all that stuff. So this is what is giving me this computation. But now what I am saying, I'll use the logistic regression. I'll use the logistic regression to fit and compare it with the basic perceptron. Okay. So this is also a linear model, just like a basic perceptron. So we have not yet moved into non-linear model. Your logistic regression is also a linear model because it uses a plus b1 x1 plus b2 x2. The only thing is that would be fitted into a logistic function to compute the probability of occurrence of a particular event. Okay. So if you look at the steps initially, the base model, we are trying to implement the base model, just the default logistic regression model. So that model, we are fitting it to the training data. We have done this earlier also, right? So just to see, these are the columns that are there. So a lot of columns got removed earlier itself because of the data cleaning process and data preparation process that we have taken up earlier. Right, the step may not be required here. Right, probably I don't want to confuse you. Probably for some other reason I would have put up that. Then we are doing the scoring back on the training data to see if there is underfitment in the model or not. Now, luckily, we have got we got 85.07%. Right, we got 85.07%. But we have seen earlier that the null accuracy is 2375 plus 453 divided by 2375 divided by 2828. So it is 83.98%. That is the null accuracy. And what we are seeing is our model, the logistic regression model, has generated a slightly better accuracy, 85.07. The null accuracy is coming out to 83.98%, whereas the logistic regression model's accuracy is showing 85.07%. So obviously it is slightly higher. So we may very well say that under bias, underfitting, right? Underfitting is not existing in this particular model. Whereas the earlier model, which is the basic perceptron model, that was exhibiting a lot of underfitting. Whereas this model is free from underfitting, because we have seen that the accuracy of the model is at least higher than the null accuracy that is associated with the model. So that is the first, which means I can very well progress this model. So it's not that I have taken a very simpler model for a complex data. Looks like the model could be an apt model. I'm not saying this model is the best model. I'm saying it's an apt model where we can look at the next steps. Okay. So in the next step, you go ahead and predict this model on the testing data. Now, because this model predicts the probabilities also, you can very well predict the model probabilities also on the testing data. Apart from normal predicting will give the final, like if the probability is greater than 0.5, it classifies into group 1, and if this is lesser than 0.5, if the probability is lesser than 0.5, it classifies the observation into group 0. So when I'm using this function called predict, the predict function typically is giving a final decision of either a 0 or a 1. Whereas predict proba is actually giving the probability of belonging to an event 1. Probability of belonging to event 1 or a group 1. That is the default. The probability of default occurring. Okay. So once I have built the model, I am testing it on the testing data. Now you could see, probably from a comparison perspective, the accuracy of this model is 85.726%. Now if I write out some of the, now I don't need to compute again. So for a logistic regression, I can very well say the accuracy is 85.726%. Right? Obviously, this is much better than the earlier model. The earlier model was a basic perceptron. I'm just comparing two models. After that, you can very well compare any number of models. So in case of basic perceptron, we got the accuracy as 79.125. So in the first, in the first metric, probably I found logistic regression to be a better model. Then I said the second metric, you can very well use the F1 score. Okay, so probably here the F1 score, which is the third one, happens to be 17.224%. Still, it is not a great thing, right? But still, it is definitely better than the basic perceptron. Basic perceptron is having an F1 score of 11.228%. So at least the comparison between the two models, I still find this model to be a better model. The third metric that I can very well use, we talked about 5 metrics altogether, right? The third metric that I can very well use is the Cohen's kappa. Right, to a large extent, I should find that the models should be definitely outperforming the other model in all the metrics. So if I look at the Cohen's kappa for the old model for the perceptron, it is 0.272%. Whereas for the new model that we have created, which is the logistic regression model, the kappa is 13.560%. So even on these lines, it looks like this model is a much better model, even in terms of the kappa estimates as well. That's the third metric. Of course, the kappa overall looks like a very, so these are all like accuracies only, but they are different ways of measuring the accuracy. And the fourth one was a balanced accuracy, which was computed even for the earlier model as well. So the balanced accuracy here looks like 54.447%. In this case, the balanced accuracy is 54.447, whereas the basic perceptron model had 50.113%. So on all the 4 counts, we could typically find that for this kind of a data, the logistic regression model seems to outperform the basic perceptron, because on all the 4 counts of accuracy, by making different assumptions, we could see that the logistic regression model has typically outperformed the other model, which is the basic perceptron model. Okay. Then along with that, here we are going to look at 2 other metrics. Okay. So apart from that, if you look at it, we have seen now here the confusion matrix is 10, 21, 18. So these 2 are contributing to the accuracy. 12 here and 161 here. So it looks like your false positives are much lesser. Right? Overall, it is not predicting, it has predicted only 30 positives. It has predicted that only 30 people will default. So that way it did not predict it. It is predicting that all of them are going to non-default only. Only 30 of them are going to default. And out of them, 18 have been very correctly predicted. Right? So this is a big problem. I mean, sometimes what can happen is the model is not able to find those people who will default at all. Only 30 people were being predicted that they will default. Whereas in the actual data, we had almost 179 people who have defaulted. But out of that 179 people who have defaulted, the model was able to say that only the 18 of them correctly. The remaining 161 of them who have actually defaulted, the model has given a different decision that they have not defaulted. Right? So that is what is the confusion matrix. Probably we may not require the classification report that heavily, but you should look at basically some of the metrics that have come out. Right? Now, the 5th metric, I have to talk about the area under the ROC curve as the 5th metric. Because earlier I have just mentioned that because it in case of basic perceptron, the area under the ROC curve. ROC stands for receiver operator characteristic curve. This is actually not, I mean, it has come from some other science into this model. Now, what is typically happening is, here we plot a graph. True positive rate, sorry, this is false positive rate, and this is called true positive rate. Okay, so I'll give you the definitions of true positive rate and false. So I'll give you one good definition that is there in Wikipedia. Yeah, sensitivity and specificity. I think this is the one. No. So here, the true positive rate, otherwise is also called sensitivity. We have already computed it. So true positive rate, you can call it as sensitivity or even recall. So the true positive is talking about how does this come? This is the true positive out of the total actual positive, which is nothing but true positive plus false negative. So out of the total people who have defaulted, how many of them have been predicted correctly by the model? That is what is the true positive rate. Then we also have something called false positive rate, which is saying out of the total negatives that are there, how many of them have been wrongly predicted out of the total negatives? So the negatives are nothing but true negative plus false positive. So out of the total negatives that are there, how many of them have been predicted negatively? Correct. How many of them have been wrongly predicted negative? Out of the total negatives, out of the total non-defaulted people that are there, how many of them have been predicted by my model that they would default? Now let's look at the numbers, that becomes more easier. So for this example, right, if I look at the true positive we have already computed in our example. In our example, the true positive, which is the recall, the recall is around 10.05%. So the true positive for this case is, let's say, around 10.05%. Okay, one instance, 10.05% is the true positive rate. Now, what is the false positive rate here? What are the number of false positives? So we could see here the false positives are 12, right? These are the total false positives. Out of the total negatives that are there, the total negatives are 1033. Out of that, 12 are false positive. So my false positive rate is 12 by 1033. So somewhere, probably if I take here 12 by 1033, it could be a point here. That's a very small value. So there will be one dot that would be plotted, because for this scenario, my false positive is this much and my true positive is this much. Now, what this ROC curve says is, you change the cutoff. You change the cutoff. So what was the default cutoff? If the value of the probability is greater than or equal to 0.5, then you put it to 1. And if it is less than 0.5, then you put it to a 0. Now what we say is, take different cutoffs. So take a different cutoffs instead of 0.5. So what do we say? If the probability value, let's say, is greater than or equal to 0.9, then put it as 1. If the probability is less than 0.9, put it as 0. So I can set right from 0.01 to, let's say, 0.99 as the cutoff. So I have different cutoffs. And for each cutoff, you plot a different confusion matrix. For each cutoff, you can create a different confusion matrix. And you will get different false positives, true positives. So you can compute different false positive rates and true positive rates altogether. Because true positives and false positives come based on the distribution of actual and predicted values of 0 and 1. So as I told you, if at all I'm changing, so the base default cutoff that is chosen in the base model is this one. But you can very well change, instead of 0.5, you can actually loop it from 0.01 or 0.001 to 0.999 kind of numbers. So you can completely loop it across and compute the false positive rate and true positive rate under each of the scenarios. Now you can very well plot a curve, because now you got different points of false positive and different points of true positive rate. You can very well plot a graph. And that curve is typically called as your ROC curve. Right? That curve is typically called as the ROC curve, receiver operator characteristic curve. So you can very well see that this is my false positive rate for various combinations. This is the true positive rate for various combinations. There could be some kind of a graph that can go something like this, right? So what is typically happening here is, so this side, it can range from 0 to 1. This side also, it can range from 0 to 1. So normally speaking, the area of this rectangle is 1 square unit. Now, what is typically said is find out the area that is enclosed by the curve. The area that is enclosed by your ROC curve. And that is what can very well be taken as a measure of the goodness of fit of the model. So this one is called measure of a kind of a goodness of fit of the model, which is otherwise called as the area under the ROC curve. The higher that particular area, the better is the model. The higher that area, the better is the model. So in this case, the area under, so and what we will, again, I'm not getting into the theory. For a worst model, right? For a worst model, which has no contribution at all, the area under the ROC curve might very well look like 50%. So it's as good as saying if the ROC curve comes like a kind of a 45-degree straight line, that is when the area is going to be 50%. So in that case, it is as good as the false positives are increasing and true positives are also increasing uniformly. So in that case, it is typically called as a random model or a useless model. It does not contribute anything. Whereas if I am seeing this ROC curve comes more along this too, right? In this case, the area under the ROC. So when the false positive, it's very close to 0. The true positive is very close to 1. So what does it mean if you look at? False positive is you have predicted as positive and it is false, which means it is actually negative, but you have predicted as positive. So that number is very, very less because you are saying false positive rate is false positive divided by false positive plus true negative. So your false positives are almost negligible, right? Which means the prediction that you have done that this particular variable, that this particular observation will not default, right? And you have predicted that this person will default, but it turned out that this person did not default. So those are the false positive cases, and we are saying those values are very less. On the other side, true positives are much higher, which means out of all the people whosoever have defaulted. So the other way of saying is people who did not default, your model did not predict default. So the model did not do a wrong prediction that they will default. And for people who have defaulted, the accuracy of your model is very high. So it has clearly specified that they have default. So that is when your true positive will be very high, even though your false positive is going to be much lower. So for very low values of false positive itself, if my true positive has come out to be significantly higher, then we can very well say that the overall area under the ROC curve is going to be much higher. And because of that, that model becomes a more and more accurate model. Now we can see that in our case, the area under the ROC curve came to 73.281%. So if I am talking about the area under the ROC curve, at least it is 73.282%. So these are the 5 metrics under which you can compare all your models. And accordingly, you can narrow down on one of the models that can come out to be the best. Okay. Now, here we may have to bring in a little bit of a different concept. One, so what has happened here? We have taken a training data. We have taken a testing data. We built a model on the training data. We tested it on the testing data. This is what we have done. Now, it might very well be possible that the model that we have worked upon, it might very well be possible that the model, so we have built one model only. We have built one model only on the entire training data. And that one single model, we have tested it on this. So sometimes what can happen, because of some input data, because of some outliers, because of some kind of thing that is present in the input data, because of some extreme value present in the input data, or because of whatever reason, that one model may not end up as the best model. Right? So this is where we have talked about something called cross-validation earlier. Cross-validation, what will happen is, right, rather than just one training data and one testing data, the same training data, I can actually get it split into multiple sub-data. So let's say if I call as 5-fold cross-validation, then my entire training data will be divided into 5 equal parts. So when it is divided into 5 equal parts, instead of one model, 5 models are fitted. Instead of one model, 5 models are fitted. So what is going to happen here? By taking, so in the first case, the first data will be a testing data. The remaining 4 will become training data. In the second case, the second subset will become the testing data. Remaining 4 will become the training data. So like that, there will be 5 models will be fitted. So each model will have 1/5 as the kind of a weightage. Each model will have 1/5 as the kind of a weightage, and we have 5 models altogether. Now these 5 models, so on the testing data now, instead of getting one probability of default, we get 5 different probabilities of default because we are running 5 different models on the testing data. We have 5 different models here. So based on these 5 different models that are run on the test data, the probability is computed as a simple average of the probabilities across the 5 models. So what we are saying here is we are building more and more authenticity and more reliability into the model. Rather than saying I'm just building one model and that particular model I'm testing it on the testing data. So sometimes the reliability may not be that high because some unique values would have come in the training data, but they would not have been present in the testing data and vice versa. Right? So what we are simply saying is, rather than one single model driving your final decision, increase the number of models. And if all the models are giving something similar, then your average score also would not be much different. So sometimes do a 5-fold. So the intention of doing this 5-fold or 10-fold cross-validation exercise is primarily the intention behind doing the 5-fold or 10-fold cross-validation is primarily to ensure more robustness into the model, more reliability into the model, more authenticity into the model. Because what is happening, the more and more such a kind of steps are being implemented. So we have instead of working on one model, we are working on 5 different models, and the collective decision of those 5 models is what we are testing on the testing data. And because of that, the authenticity of the model is going to increase. Right? So the cross-validation, we have a function called cross-validation. So we can actually do a kind of a scoring of, so let's say here we are saying we'll do 10-fold cross-validation. And we will look at the cross-validation accuracy. The scoring can be done based on accuracy, or the scoring can be done based on balanced accuracy, or the area under the ROC curve. So you could clearly see, if I look at the ROC, if I look at the accuracy for 10 different subsets, I could see that the accuracy is more or less similar, 85, 84, 86. In some cases, it has even gone up to 86. In some cases, it was at 84. On an average, it was at 85.4. Similarly, when you look at the balanced accuracy, that also ranged between 54% to almost 56.7%. And similarly, the area under the ROC curve also There were some subsets where the area under the ROC was even 79%, whereas there were a few subsets where the area under the ROC was only 68.9. So what we are saying is to get more and more robustness into the model, rather than running one model on the entire training data, run multiple models on the subsets of the training data, and based on the output that they have, multiple subsets have given, you go back and try to do the testing on the testing data. So that is one more exercise which is called cross validation, which we will see in the final model, right? But the intention of cross validation is very clear. It will help me in terms of identifying more and more robustness in the model. Then there is one more element. I don't know whether we should treat it. Are we okay if we do it now? This is a slightly complex concept, but if you are okay, but it will not take more than 10-15 minutes. So if you are okay, I will deal with it today. Otherwise, we can take it to the next class. The hyperparameter tuning. Or let me take it, if it is not a kind of overload, I think I'll take it so that we can finish the logistic regression today. Okay. So we have something called hyperparameter tuning. Now, in this hyperparameter tuning, what is going to happen is we have two types of parameters. One set is the regular parameters, and the other set are called hyperparameters. What is the difference? The regular parameters, they are determined by the model. For example, the coefficient. We said y hat equal to 1 by 1 plus e to the power minus z is nothing but a plus b1 x1 plus b2 x2 plus and so on bn xn. Now, what should be the values of a, b1, b2, bn? That will be determined by the model. The coefficients will be determined by the model by minimizing the error or something, log loss function, error. So they are determined by the model, and they are called regular parameters. Whereas when it comes to hyperparameters, they need to be fixed before running the model. They need to be fixed before running the model. Right? So they are not determined by the model at all. The model assumes these values for the parameters and then executes the model. Right? So the parameter values are assumed, and those are called hyperparameters. So for every machine learning model, there are a set of hyperparameters. So what we generally do is we do different iterations, wherein in each iteration we take different combinations of those hyperparameters. For example, in case of logistic regression, if you really look at the function of logistic regression, I'll tell you. So you go with the scikit-learn logistic regression, right? Which is this one. So if you look at it, It actually talks about some parameters. And all these parameters that it mentions here, they are all hyperparameters. You have to fix some value for each of the parameters. Now, if you look at this, the first parameter is penalty. So for penalty, do you want to go with L1 penalty, which is lasso? We discussed about these various penalties earlier. Lasso is the L1 penalty, absolute value of the coefficients. L2 is the ridge penalty, which is the squared value of the coefficients. Elastic net is a weighted average between the lasso and the ridge. So what is happening is logistic regression can very well be executed by putting the penalty also into it. And there is a none as well. So there are 4 different kinds of penalties that are supported. But if you see this model, by default, it takes L2 penalty. But it can very well be possible that if I make the model assume an L1 penalty, or if I make the model assume an elastic net penalty, or no penalty, it might be possible that the metrics of the models could be much higher as well. So that is what we are going to talk about as hyperparameter tuning. So if we really look at this model here, so the one of the hyperparameters that we are talking of is penalty parameter. So by default it takes L2, but I want to try all 4. I want to try all 4 and I want the model to decide which one is the most appropriate for this data. Similarly, there is one more hyperparameter called C. You see here, C is one more. So we list generally the most important such kind of hyperparameter. So this is called inverse of the regularization strength. Smaller values specify stronger regularization. So again, we take some values. By default, it takes only a value of 1. But we want to test out if we change the values, let's say to 0.01 and 0.1, making it more stronger regularization. Or if I make some weaker regularization by giving the values of 10 and 100, I want to check all possible combinations. And similarly, the third mechanism that I can think of is fitting of the intercept, which is that A plus B1 x1 A. So by default, the fitting of the intercept is true, but it can very well take a false as well. So what we say is try out all possible combinations of the initial assumption. Hyperparameters are nothing but initial assumptions for running the model. So by default, the default model considers some values, right? But what I want to see is if I change that combination, what is going to be the result? Is there any improvise? So basically, I am taking 4 different values for penalty, 5 different values for C, and 2 different values for fitting the intercept. So basically, the permutations and combinations talk about 4 multiplied by 5 multiplied by 2, 40 different combinations I want to test. And I want to see which one is producing better on the various metrics. So we are trying on accuracy. We are also trying on balanced accuracy. And we are also trying on area under the ROC curve. So on all these 3 counts, we want to see which of these 40 assumptions regarding the initial parameters of the model are resulting in a very high accuracy, are resulting in the highest balance accuracy, resulting in the highest area under the ROC curve. So we are fitting all the 3. And finally, we could see that when I'm going with the best parameters based on accuracy, it showed that you take a C value of 0.01. The default is 1, let me remind you. So it says rather than 1 for this problem, you take the C value as 0.01. Fit intercept is true. And penalty is no penalty. The default was it has taken L2 penalty. But now it is saying don't take any penalty. That one is better if you are going with accuracy. Probably I'm not much based on accuracy. I want to base it on balanced accuracy. As we have discussed, if the data is having a lot of imbalance in it, more than the accuracy, probably balanced accuracy could be a much reliable measure. So even the balanced accuracy concept says C value go for 0.01 only. Fit intercept make it false and then put fit intercept, you make it false and then put a penalty of L2 penalty. Right? So L2 penalty is the default. But C1, C value, it has changed and intercept value also, it has changed. So it says that this combination is going to give the best. But if you are using area under the ROC curve as the best one, you could see that C value has been made as 10. So basically what is that is happening? There are 2 or 3 models that are coming as competing models. I mean competing combination. So you can very well decide which this thing you want. You can very well decide which metrics is what you are more relying upon. So probably you can think of the balance and accuracy kind of a metric or any metric. So based on that, you can very well give the parameters. So it is not so one here. Probably if I go with balance accuracy, it has to be 0.01. Fit intercept is false and penalty is L2. Based on that, you can run your model. And surprisingly, so by doing this, I think I have done it with 1. I should do it with 0.01, but now it is running somewhere. So probably this part has to be reworked upon. So then you can very well compare your accuracy, your balanced accuracy, and then you can say which model is the best fitting or which, I mean, that is the metrics that you can associate with your model. So we are getting a very high Cohen's kappa. Now you could see here, the Cohen's kappa for the model has become 19.76. Earlier when you did this exercise, it looked like Cohen's kappa is, okay, Cohen's kappa is 13.56, but now it has gone up to 19.76. So it looks like some performance improvement has come. Overall accuracy would have gone down, but balanced accuracy has definitely gone up because our objective was to maximize the balanced accuracy. And we are seeing that the balanced accuracy has gone up by doing this kind of a exercise. So sometimes what happens is, depending on our objective, though some other aspects will get slightly compromised, but overall we might build upon the overall goodness of fit of the model. You can see the Cohen's kappa has increased, which is what is one of the measures that we would typically look at, especially when there is a lot of imbalance. Even the balanced accuracy has increased. So by doing this hyperparameter tuning along with the cross validation, it might very well be possible that in some cases we might improve upon the overall goodness of fit of the model. So that is what it is about the logistic regression. And we will work out on a couple of other models in our upcoming class. So we don't have a class tomorrow, I think only the next week, and I'll communicate the next week's schedule, possibly before tomorrow, to Ravindra, so that he will share with you share with you the schedule for the next week. Please provide notes on accuracy. I don't have any kind of notes. I don't prepare much of a notes. right? I would always better speaking out, but yeah, you can very well refer to some. So accuracy of model building. We have been talking about the accuracy, right? Accuracy is true positive plus true negative divided by the total data. So while we keep on doing with the other models, I think you will get a lot more comfort as well. All right, or a simple internet articles should do, because there is nothing much technical in the accuracy, right? But those 5 metrics is something that you should be very clear about. All right, so we'll do a quick you do a quick revision up to here, right? And probably you can come back to me in the next class. In case anyone is facing issue with any of the aspects, I'm sure I'll spend some more time, because from here onwards, it's more about the different kinds of models only. So we'll have k nearest neighbors, we have all the other different algorithms. The mechanism is exactly the same. So you'll not find much of, after that, it's more like a smooth flow itself. Only a little bit of mathematical part as to how this model is performing in the back end, right? From here it would be a similarity. There's a lot of similarity in the execution. So if you are getting a comfort with respect to executing the first one, you will get the comfort with the remaining ones as well. So I'll save this, and possibly I'll share this